Hello everyone. In this tutorial, we will go through the caret package in R. Now, caret is a wrapper package for more than 240 machine learning algorithms in R. The problem with these algorithms is that they are coded differently. They have a different syntax. They may expect the outcome variable to be coded in a certain way, and they have a variety of options to do hyperparameter tuning. It can be very confusing to keep track of what code, what syntax any particular package requires. For example, in doing logistical regression, the GLM package requires that the first level be the failure class, while the second level be the success class. So 0 versus 1. Some packages expect the first class to be success and the second class to be failure. So they expect the output to be in 1 versus 2 levels. So this is really confusing as to how to know what way your output should be coded. Caret removes some of these obstacles. In caret, there is a unified syntax for more than 200 of these packages. It is a very powerful framework which lets you do some of the basic pre-processing tasks with your data. It allows you to split your data in training versus test. It lets you resample, carry out k-fold cross-validation. It also lets you train your model using these various algorithms. And then to switch from one to the other algorithm, it requires minimal change in code, as well as it provides a variety of metrics for evaluating the predictive performance of your model, as well as the classification accuracy of your model. So let's take a deeper look into how caret works. And once we understand the basic structure of the way caret is used, we can change the models to whatever algorithm we want to run very easily and with very, very minimal change in the code. The dataset for this tutorial will come from the textbook Machine Learning for Business Analytics. And you can download the dataset from the textbook's website using one of the co-authors' GitHub page, or I have a fork of that repository which has only the dataset. So you can run any of these commands. You need to install the DevTools package first, and then you can obtain the dataset that we will work with. So some of the libraries that we will use are caret, tidyverse, lattice, and MLB data. We will work with the Universal Bank dataset. That dataset has 14 variables, 5,000 observations. We will just do some preliminary cleaning on this variable. Notice that our variable of interest is personal loan, which imports as an integer. We need to convert that into a categorical variable with the target class being 1. So we can make those transformations here. Notice that in caret, the expected setup is that in a binary classification model, our target class is 1 and the failure class is 2. So the first class is a target class. So we are releveling our data set to have yes or 1 as the class of interest. So we have 2 levels, yes and no. So once we run this through caret will then target our success or yes as the outcome variable. We also see that education has been transformed to be a categorical variable. Next, we can partition our data. Caret makes it very easy. There's a function called create data partition in which we can set aside a certain part of our data set as training on which the model will be built. And then we will have a test set on which we can see how well the model did. To replicate our results, we'll just set the seed. And once I run this, it creates an index of row numbers randomly chosen so that 80% of the rows will go to the training set and 20% will go to the test set. Now, one advantage of caret also is that this is a data set in which the number of successes or yes occurs only 10% of the time, or 9.6%. So if we were to randomly do an 80% sample, it is possible that our training set may not have any occurrences of our successful outcome. So once, then that will make our model building process not very meaningful. So create data partition has an option. We can specify our outcome variable, and then it will maintain the ratio of the success and failures in the main data set in both the training and the test. So we can see that in our training set, we again have a 9.6% success, and so in the test set. So this is a very helpful function, create data partition, which does better than just a random sampling. The next step in the model building process usually involves some sort of pre-processing. Caret again provides several routines to pre-process the data. Suppose you had a lot of variables which were highly correlated. Caret has routines which can help identify highly correlated pairs and then remove one of those variables. And it also has options to transform your data. Now, one big issue is whether you should transform the data after you have done the training and test split or before doing the training and test split on the entire data set. For that, know that the test data set function is to basically assess the quality of the model built with the training data set. So test data set is typically unseen, it is untouched in the model building process, and is only used to check how well our model was. So nothing we do in a model building process should be affected by the test set. As a result, the convention is to first split your data set, apply the transformations on the training set, and then use the same parameters to then transform the test set. One common transformation is to standardize the data. In R, it is called center and scaling. So by centering, you're subtracting the variable, the mean from the variable, and then by scaling, you're dividing it by the standard deviation. So in standardization, we have these two parameters, mean and standard deviation. So the process would be that you first find the mean and standard deviation of your variables in the training set, transform the training set, and then use these same parameters to transform the test set. So your test data set may not truly be standardized, in the sense it may not necessarily have mean 0, standard deviation 1, but it will still be close enough. And also it will keep our test data set pure from the model building process. So we can do pre-processing in caret in two ways. Caret has a built-in function called preprocess, which will help us do the transformations. So we call the preprocess function with the arguments of center and scale using the train set, and then we will predict. In caret prediction, or predict is used to then implement the routines built in the main function onto the data set. So it will then basically, it won't predict anything, but will just transform our training and the test set. The second approach that caret allows us to do pre-processing while running the train method. We will discuss this a little further down. So let's do the first approach. We use the preprocess function on the training set, and the methods we will use will be center and scale. So now it will create an object with the mean and standard deviation of each of the variables. We will use predict to then transform our training data set. So the first argument is the object. The second argument is the data set over which we want to carry out this transformation. So this will now transform or standardize our training set. And then we'll apply the same object, our train.vals object, on the test set. So now our test set is also transformed. If we look at this data set, the test set, we see that all our continuous variables have been transformed except for education, because education was the factor variable which did not get transformed. And of course, our personal loan, which is our dependent variable, did not get transformed. But everything else has been transformed using the parameter values obtained from the training set. Now, The most important function in the caret set is the train function. This is the workhorse of caret. Train lets us do three things. It lets us evaluate using resampling. So there are several methods, including bootstrapping, cross-validation, repeated cross-validation, k-fold cross-validation that we can do, which will essentially split our training set into multiple samples, run the model on each sample with certain variables held out, and then predict our outcome on the held out sample, and then repeat that as many times we want to repeat, and then give us the results by averaging the performance on all these held out samples. As a result, it will help us choose the optimal model parameters. And then it also then helps us assess, or has built-in functions which will help us assess how well our model does from the training set, and we can then use it to predict our outcomes in the test set and then also assess the accuracy of those models. So the train function is a wrapper function. It will help us run various algorithms, whether we are doing binary classification or we are doing prediction using regression-based approaches, and then help us compare our results among different models. We'll illustrate how to use the train function by running a basic logistical regression model. Logistical models are pretty straightforward. There's no tuning involved. And then we will also see how we can use the train function to do some hyperparameter tuning using a penalized elastic net kind of regression, logistical regression model. So for the basic regression model, we'll first set up the trainControl function. Now here, the trainControl function will tell us what kind of resampling we want to do. Let's say we wanted to repeated cross-validation or k-fold sampling. Here we will do a 5-fold, that's what the number tells us, and then we'll repeat it 3 times. And then there's another neat feature in caret. It allows us to do parallel processing if possible. So we can just set that flag by saying parallel processing as true. And because we want to replicate the results, we will just set the seed before we create these samples. Now, this code chunk shows the setup of the train function. This will stay the same no matter what algorithm we are using. In this case, we're using the formula interface. We are specifying our dependent variable on the left, and then we are running it as a function of just 3 variables, let's say age, income, and credit card. So in the next argument, we specify the data set that we're working with. This is the train data set. And this is the crucial argument. This tells us what method we're using. So in this case, we're using the GLM method. As I mentioned before, GLM method expects the outcome to be the second variable, but caret has unified interface. It expects the outcome of interest to be the first variable. And that's why we did the releveling in the beginning of the process. And then family binomial will then tell us that we're doing generalized linear modeling, within which we will do the logistical regression. And then this is what we'll call out the kind of resampling that we will be doing, the trainControl function. And then we are just calling here on the function that we defined above, the fitControl function here. So we can run the model based on our 5-fold cross-validation done 3 times. So it says 5-fold cross-validation, we repeat it 3 times. And based on what the model ran, the accuracy was 0.9. And these are our estimated coefficient estimates. So this is a simple logistical regression model. There isn't any model tuning going on. It is just a basic regression setup. Now, the default metric on which it assesses the parameters is accuracy in a classification problem. Accuracy basically looks at how many cases were classified as 1 versus 0 and compares that to the actual 1 and 0 cases. But Another metric that is used very frequently in analytics is the ROC, or receiver operating curve, and the area under the curve. However, the ROC curve requires the output to produce the probabilities assigned to each of these examples or samples. So by default, we only get predicted classes, we don't get the probabilities, but we have to make some changes beforehand, which will enable us to get the class probabilities for each of these cases. So in the trainControl function, we can add a couple of arguments. We can say class probabilities equals true. In this case, we will get the probability assigned to each sample, what is the probability between 0 to 1 that it is of a certain class. And then we can also get a bunch of summary functions using the toClass summary flag for the summary function. So once we run this as a trainControl function, we can now change the metric to ROC. So again, the structure of the train function remains the same. We have our model, we have the data set, we have the method, and now we add metric as ROC. And we can again examine the results of this specification. And our area under the curve is 0.91. So it's a pretty accurate model from what we have. Again, we have our coefficient estimates. They're very similar to what we had before. We had minus 0.09 for age, minus 1.70 for income. Here we have minus, so pretty much very similar results. Now, once we have this model, we can use it to predict our outcomes on the test set. And then we can also assess the accuracy of our model compared to the actual outcomes. So we can use the confusion matrix function. So first, let's do our predictions on the test set. In the confusion matrix function, the first argument is the data of interest. This is our predicted class. And then the second argument is the reference or the truth class. So our truth is the personal loan variable in the test set. And our predicted class is what we just predicted using the model we ran on the training set. So the confusion matrix tells us that we had quite a few correct predictions. In fact, our accuracy was 0.91%. We had 33 cases that were correctly identified as yes. We had 873 cases correctly identified as a no, but we had some misclassifications as well. Now, as I noted in the previous setup, we did the transformation beforehand instead of doing it afterwards, but the train function allows us to do pre-processing in place as well. So here we will run logistical regression on the main data set without doing pre-processing beforehand. We'll call pre-processing within the function here. So the only difference here is that we are still using the same fit control. We are still using metric, ROC, but we are doing pre-processing in place. So here again, our ROC is 0.91, which is what we had gotten before as well. And our parameter estimates are very similar too. We can actually look at our predictions on the test set using the second model. And our accuracy rate is again 0.911. If you want to compare the outcomes from both doing pre-processing beforehand and doing pre-processing afterwards, we see that we get the exact same predictions. So whether you do pre-processing as a separate function or within the train, I think it depends on the context of the problem. If you'll be working with transform data for further analysis, it might be good to do it as a separate step. If some models require standardization of data while others don't, you could do that within the train function. Now, where I think caret really outshines us in the idea of building or letting us find the optimal parameters through hyperparameter tuning in logistical regression model, there wasn't really any tuning going on. We had a simple set of variables and we ran the model regressing our outcome on those independent variables. But suppose we had a large number of variables and we wanted to impose a penalty on how many variables we include. So the logistical regression is captured by just the first part of this equation where it's maximizing the log likelihood. But let's say that we add a penalty on number of variables included. So the first part is like the ridge regression and the second part is lasso. And here we have two variables which control the penalty. One is lambda. The extent of lambda shows how much penalty is given. If lambda is 0, we're back to logistical regression model. If lambda is 1, then there's a very high penalty given to the number of independent variables that we add. And then alpha is like a mixing variable. It shows what is the share of, if alpha is 0, we are then in the ridge regression framework. If alpha is 1, then it's a lasso regression framework. So alpha controls the importance given to ridge versus the lassos, which is like the elastic net framework. So in tuning, we want to find the optimal value of lambda and alpha that we need. So we can do that using our tuning grid. So we are creating a grid where we are letting the model determine between 10 different values of alpha ranging from 0 to 1. So they'll be controlling our mixing between ridge and lasso. And then we'll also want to tune over lambda. So we're creating a sequence of 20 values from 0.01 to 0.3. So that'll show the weight given on the penalty. So if we run this, expand grid basically creates all combination of these values. So we see that there is a space of 220 variables that will be tuned by the model. So to run that, we will use the GLMNet model. And you notice how easy it is to change the methods within train. We just say that method now is GLMNet. Earlier we had method equals GLM. We said family binomial. We can change to a much more complicated model by just making a change in the one line of code. We'll still preprocess our data. We will use our tune grid that we just created, and we will use our trainControl function that we had defined earlier. So all these stay the same. The only difference is now that we have a new method here, GLMNet. So now caret is running a 5-fold cross-validation, doing it 3 times, and iterating over 220 parameter values using parallel processing. So it's going to find the optimal value of our alpha and our lambda. And then we'll run the final model based on these tuned values of alpha and lambda. So again, just to recap, I had paused the video because it was taking a while. The model was searching among the space of 220 possible parameter combinations of alpha and lambda. It did that using a 5-fold cross-validation and repeated that 3 times. So based on that, we get this list of parameter spaces that the model ran over. Then we get the ROC measure for each of these. And the highest ROC was obtained with alpha equals 0.1 and lambda equals 0.01. So if we go back to our equation, there was a very slight penalty imposed on the number of parameters, and alpha being 0.1, there was a much heavier weight placed on the ridge type of penalty versus the lasso type of penalty. Now, lambda being small indicates that we really were not penalized for having too many variables, but that's because our model had a few variables to begin with. We can look at the number of predictors that were run in the final model by using the predictors function. And this says that it pretty much ran all the models that we had in the data set. They were all included in our estimation equation. Now, one drawback with these more complicated models is that while we can see what variables were included, it does not give us parameter estimates like we got in the logistical regression or what we get in regression-based models. So that makes it difficult to interpret the results. It becomes more of a black boxy algorithm where we can assess the outcome, quality of predictions on the test set, but we do not know what these variables mean. So caret has an important function called varImp, which is the variable importance. This will help us figure out what variables had a higher role to play in running our model. So if you look at the varImp, we get that income had the highest weight, followed by education or advanced level, then the grad degree, then whether the person has a CD account, family, and so forth. So in the absence of parameter estimates, to have some business interpretation from our results, variable importance plot becomes a really important tool, because now this provides some business context and being able to derive some business insights from what our results are. Now let's obtain the confusion matrix based on the predictions from the training set on the test set. And we see that our accuracy is 0.95, which is a little higher than what we had for the logistical regression. Of course, we have more variables, but then we also had a penalized model. So here we covered, in a nutshell, details of the caret function. We started with seeing how caret can help us do a data partition between training and test set. We also saw how we can do pre-processing both before we run our models or while we run our models. And then we also saw how we can decide what kind of resampling we want to assess the best optimal parameters that we get, whether we can want to do repeated cross-validation or k-fold cross-validation. There are other options within the trainControl function that caret allows. And then finally, we saw how we can, just with very little change in the code, run models from our simple logistical regression model to a fairly complicated elastic net or penalized logistical regression model. And how caret lets us choose the optimal parameters from a fairly large hyperparameter space that we gave it. And then how we can assess the accuracy of our classification using the confusion matrix. We will, in the next video, see how we can dig deeper upon how to evaluate our model accuracy using the confusion matrix, and then get some other measures of accuracy for binary classification as well as regression models.